Hi, we're going to now look at a derivation that's going to be very important to you on the AP exam. The starting point for this is page 162 of Survey, but Survey does kind of a halfway job of deriving this function. So you need to know this, and you should pay attention to this video, maybe look at it a couple times, look at the posting, the document I've put on Blackboard about this. So let's just suppose we have an object in motion. It's falling and it has two forces acting on it, gravity and this resistive force which is proportional to its velocity. Okay, by the way, this is not the way air resistance works. Turns out air resistance is proportional not to velocity but the square of velocity. But let's suppose we have this resistive force R that's proportional to the velocity. So R equals negative kV. Okay, well then we can say the summary of the forces on this object, which are equal to ma under Newton's second law, and also equal to m dv dt under our calculus view of what acceleration is. The summary of forces then, m dv dt equals mg, the force of gravity, minus kv, this resistive force. Okay, well here's the challenge. Derive a function for velocity in terms of time that takes into account these conditions. You need to remember this derivation, look at this document online, because this very likely could be on the AP exam, or variants of this derivation. Okay, so again, the summary of the forces equals ma equals m dv dt equals mg minus kv. Okay, well let's divide everything by k. So we then get this expression m over k dv dt equals mg over k minus v. What good is that? Well, that putting the expression in that form allows us to do our first trick. It turns out that mg over k is the same as the terminal velocity, which we're going to call vt. How do we know that? Okay, well take the equation that we had for the net forces, mg minus kv. At terminal velocity, the balancing, or the resistive force is going to be exactly balanced with the force of gravity. They're going to be the same as each other, so mg minus kv is going to be equal to 0. Well, if mg equals kv, then we can say that the terminal velocity is mg over k. All right, so we at terminal velocity, mg equals k times the terminal velocity, and therefore the terminal velocity equals mg over k. Okay, so we now know a different way to say mg over k, and we're going to substitute that into the above expression so that we now have mk dv dt equals the terminal velocity minus the velocity, which sort of makes sense. What we're saying is the acceleration, or the change in velocity with time, does amount to a difference in velocity. As we get closer and closer to the terminal velocity, that difference between the terminal velocity and the velocity at a particular time is going to get smaller and smaller, and eventually the velocity is going to approach the asymptote of terminal velocity. Okay, well, so let's remember that expression. We're now going to go to page 2, and we're going to carry over that expression. All right. Now that's a differential equation, but don't be afraid of it. Notice that dv and dt are very small, even infinitesimal, but they're not 0. Since they're not 0, we can multiply or divide by dv or dt as we see fit. And so let's see how we can do that. Well, in order to integrate this differential equation, we're going to take this expression and we're going to separate the variables. Okay? So we've rearranged the above equation to put all the dv and v stuff on one side and the dt term on the other side. All right? Now, we can integrate both sides now, but before we integrate both sides, let's take that vt minus v and simplify it and call that expression just u. We have a new expression u which equals vt minus v. And as we usually do when we do a u substitution, we not only define u, but we find out what du is. And if we if we differentiate to find du, we see that the differential is just negative dv. Vt is a constant, so it drops out of the differentiating. Okay, so let's plug in u and du into the equation we had, and you can see if we substitute those, we come up with a new expression, a new equation that we're now going to integrate. Okay, so the limits of integration are from, on the left-hand side, from 0 to u, on the right-hand side from t equals 0 to t. That's permissible to have different limits of integration as long as they correspond to the same point in time. Okay, so we're going to integrate negative 1 over u du, and we're also going to integrate the right side, which is very simple integration. So when we integrate negative 1 over some function, what we get is the negative log of that function, and again we're expressing the limits of integration from 0 to u. Okay. Let's just switch the negative sides. So now ln u from 0 to u equals negative kmt. We went ahead and integrated the dt, which when integrated just becomes t. Okay. Well, let's reverse our u substitution. So instead of ln u from 0 to u, we're now going to have ln vt minus v, and we're changing the limits of integration to 0 to v. So you can see that expression when we calculate that definite integral over those limits of integration. Here's what we get. Using our rule for logarithms, when you subtract a log, it's the same as dividing, so that expression is the same as this. Okay, let's exponentiate both sides. And you can see how we've exponentiated both sides. If you need help on that, see me, or we'll go over it in class some more. All right, let's multiply both sides by vt, which we've done there. Let's rearrange to isolate v, so v equals vt minus vt times e to the negative kmt. Okay, and here's our final answer. That is the function we were looking for, the function of v in terms of time, and that's our answer, QED.